name is Marlos, and today I'm going to talk about uncertainty estimation in the meridional overturning and heat transport, meridional heat transport across 35 South. This is where we have the AX18 transect, XBT transect, and the objective is to estimate the uncertainties on this transect. So this is a summary of two recent papers that we have accepted here with my collaborators, Molly Berenger, Gustavo Goni, and Shimfu Dong. So, first we need to know why to study the uncertainties in this transect. First, this is the longest time series we have on the meridional overturning transport in that region, in the region of around 34 South, and since 2002 until the present. And here's from our web page where we have always updated the estimates of these transports. So the XBT measure temperature in the top 800 meters, where the rest of the information all the way to the bottom and salinity and other aspects have also been inferred. And and also there's a decomposition here of Ekman, geostrophic, and the total transport, and they have some characteristics studied of its seasonal variability that from a few transects, and we have tried to estimate the seasonal variability of these properties, and you see that in general there's the geostrophic and the Ekman transport are in general out of phase. So yeah, so to study the heat transport is important because this is part of the meridional overturning circulation, and then we have the ocean carries a lot of the heat that we have globally. And so I'm not going to go too much on the introduction because recently Shimfu and René gave really good talks on explaining all the observational efforts and the aspects of this. So I'm going to skip most of this part because they talk much better than I do. So some of the assumptions that I said we have to use to estimate these integrated transports across the section is first on the salinity on the top of the surface and on the bottom temperature below 800 meters, the geostrophic velocity, all the assumptions we have to estimate geostrophic velocity, reference level velocity, and and also on the operational aspects of these estimates, like the zonal sampling and the time sampling. So these are all aspects that haven't been studied deeply. So there's actually only one study that I'm aware of, is the Berenger and Gazzoli 2007, that they estimated only for the meridional heat transport uncertainties due to some of the assumptions that we have to estimate this transport. And no sensitivity has been yet performed to estimate the volume transport or the meridional transport part of these estimates, and also all these observational and computational approximations that we have here. So this is the motivation for this work. So the objective here that for this talk, we're going to focus on a few examples on the uncertainties that we addressed. One, the horizontal sampling, the temporal sampling, especially on the seasonal cycles. That show that the first figure is one of the aspects that we care about, and the salinity and deep temperature estimation, and the reference levels, especially on the barotropic part of the geostrophic approximation, and also And the last point is how the XBT measurement biases could affect the estimate. So from this last point, I want to motivate here, and that from the heat content aspect, the global heat content. So we have a long time series all the way to 1955, and we have, for example, this estimate from last to 2009 where they corrected the XBT bias, and before in 2005 where they hadn't corrected the bias. So these bias were the cause of most of these decadal variability we used to see that the models couldn't capture, and we see that all was on the observational part, but on the meridional heat transport, no work has been done to estimate this aspect. So this is something we're going to address. So for this will be complete a model study where we simulate the observations inside the model framework. So for this, I use the HICOM global analysis. And so we have daily outputs of the global analysis. Unfortunately, by the time of this work, we had only available from 2007 to 2013. Now they released the reanalysis all the way to 92, but we had to do some approximations here to extend this time series. And it's an eddy resolving model with 32 vertical levels with the no-gap fluxes on the surface. And it assimilates most of the observational data we have. So a little bit of validation of the model. We see a good way to look at the model energy axis is just the eddy kinetic energy and compared to for example, the aviso data and sea level height variability. And this is the HICOM and this is the aviso. And this is where our transect is located. So we can see that the model captures most of the features of this mean eddy kinetic energy aspect, even though generally we see that they are biased toward less variability in these high eddy kinetic energy regions, such as the Zapiola eddy and the Brazil-Malvinas confluence and the Agulhas leakage. And in general, here's in a percentage change. Generally, there's an underestimation of the variability in these regions and overestimation where there's low eddy kinetic energy. Also, to compare how the model stratification, how it compares, for example, with the XBT and the climatological values. So we compare the model here with the observations. And here's altimetry again, it's the same information as we had before in the RMS of the sea level height. And we see that the model generally underestimates the variability in this region. And here is comparison to the XBT data until 800 meters and below to the climatology data. And you see that generally the model has a higher stratification here, and then we have a low temperature bias generally, and then the observation seems to have a more linear relationship here from west to east, and the model has these different features. So, yeah, in general, it agrees with the observation. So how are we going to simulate the observations and the X18 in the model? But we are going to try to do the same assumptions as the observational part. So for the salinity from 0 to 800 meters, we use a TS lookup table that was controlled for the model environment. And from 800 meters to the bottom, also the model climatology, we just added the climatology below 800 meters. For the temperature, it's the same as we use a padding below 800 meters. And for geostrophic velocities, we use generally a reference level at the sigma 2 at the 2,000 meters, reference at 2,000 meters, at 37.09. This is generally what has been used in observations, and I believe this comes from Gonna Show in Wunsch paper, 2001. And the time sampling, as I said, is generally quarterly, and we are going to test how this is effective to capture the seasonal variability. And also the spatial sampling, which is generally, we have this heuristic approach to have put a higher resolution in the boundary at the currents are stronger, and in the interior, we generally 50 kilometers. So these are we are going to test a few of these aspects of So and then we simulate this observation, and then we need to reconstruct the model velocities. So in this work, we used a velocity decomposition that is generally being applied a lot in the rapid data, in model analysis in the rapid data. So where the velocity is decomposed into three main components. One is the barotropic, that is related to the depth average velocities. The Ekman part is calculated directly from the zonal wind stress, plus a component to estimate below the Ekman layer. So it's a kind of a return flow below the Ekman layer here, and the vertical shear component. And of course, there's a residue here. Generally, this residue is what this decomposition can't resolve, so the hydrostrophic and other parts of the flow. So the vertical shear is generally associated with the geostrophic calculation itself, minus a vertical average term. So vertical shear has no vertical average component. And the geostrophic velocity is calculated from the classic thermal-wind relationship, and we can add a reference velocity to where it's referenced. So if we don't add this, would be a no motion at the reference depth, and then if we add this velocity, it would be referenced to that velocity. And all these components are compensated to allow zero mass transport across the transect, and this is really important, especially for the heat transport component of the flow. So a few of the parameters the metrics we're going to use here is for the AMOC stream function, that is just the integral of velocity from west to east and from the bottom to the surface. And the AMOC strength is the maximum of this integrated stream function. And the meridional heat transport, that is, we integrate the velocity times the temperature over the transect. And also we have here this term to exactly to allow zero mass transport that we generally are not going to use, because as we define our components, they have zero mass transport by definition. So to reconstruct the AMOC, and this is a validation for our method of the reconstruction. So we see that in black here is what the model, we estimate the AMOC for the model velocities. And in magenta here is what the total reconstruction is. So we see that's pretty much on the top. And of course, it has this high frequency variability here that could be done to a geostrophic part of the flow that can't resolve by this methodology. And this is how the vertical shear is generally in the mean, compensates the barotropic part. The barotropic part is generally negative. This is the strength of the stream function. And this is the Ekman part. The Ekman part generally has almost zero mean flow, but it has a strong variability as well. And this is how the stream function, the mean stream function, how it compares with the reconstructed, is pretty close to what the model gives. So, yeah.
Data here, is it observation?
No, all models, this whole work.
All the model and the facility you reconstructed.
Yeah, so this is what I call, good question. This is called the perfect model reconstruction. So I use all the information of the model at all locations and using the reference velocity, the models as a reference velocity, similar to what I think when so this is what we are going to compare against when we have the approximation.
So why are they so different at times from the real model MOC and the reconstruction? And it's perfect model data, right?
Yeah, but we have this geostrophic reconstruction, and I think that the geostrophic part can't get the full variability of the model.
But sometimes they're different by converters in the complexity of the
Yeah.
Is that big?
Yeah, no, because this model, the data I'm getting from this model is every 7 days in 7 days average. So we have this strong variability of the model in this time scale that are still there.
It's high comfort layers, or
Yes, it's interpolated to 32 layer model. So this could have also effects on of the proper simulation processes and things like that. So yeah, but yeah, in general it matters. But yeah, of course, I think you were right. In certain points, it doesn't get the whole variability.
But I guess you compare each the individual regions, so you can figure out where the transports were most different, where the boundary regions, or something like that, right?
Right.
What those errors, where the errors are coming in the calculation. So that's
Right.
really interesting. More belief.
Right. No, I think yeah. I had done some of these before. I was using daily data. But daily data we could have like a 40 variability there from one day to the other. So the model is really high. So I put 7 daily outputs, but yeah, you still get a lot of variability. And so in comparison to the data from Dong et al., we see that the model generally underrepresents the strength of the AMOC, and so the variability of the model, because you get in these time scales, is almost 7 value as a standard deviation. And the same thing for the heat transport. And the heat transport, the difference are even stronger here in comparison to Garzoli et al. 2013. And we see that the geostrophic part is about half of what is estimated by Garzoli. This is, I put a still here because this is estimate from the residual between the two here. I don't think in that paper they put exactly the value. So in terms of the climatology, too, is good to it has been used to assess the model variability, and so the model has the seasonal cycle here in the total. The vertical here has almost no seasonal cycle, and the barotropic part has a strong seasonal cycle too that agrees with the Ekman, so they kind of enforce the total seasonal cycle of the model. And the geostrophic part is generally in phase with the Ekman. So this is different than what it has been studying in the observational data using XPC. So let's go to our main point of the paper there, uncertainty quantification. So just as the effect of salinity and deep temperature estimate, as I talked before, we use a lookup table in the upper 800 meters and a padding underneath that. So this is how a lookup table, so is the RMS against the real salinity in the model. And you see that for the lookup table, I use annual data instead of monthly. So we can see that most of the variability is due to the seasonal cycle. And this is what you look at when you look at the residues of the AMOC and heat transport against that perfect reconstruction using padding, lookup, and padding plus lookup. So this will be the full XBT approximation that you use in observation. So we can see that generally padding bring no bias, no mean bias, and the lookup is what caused the whole bias here, both in the heat transport and the AMOC. But in general, the variability, they are pretty similar, so they both contribute to the total variability. And well, the point I want to make here is that the lookup, when you see in terms of a seasonal average of the residuals, you see that this strong component, seasonal component, when you use just annual TS lookup. So it's important to use monthly TS lookup or even real salinity for that. When you see that the padding has almost zero biases in seasonal average. So for the time sampling, so the question here is how a quarterly sampling would address the seasonal variability of the AMOC and heat transport. So here are all the sections we have. I think this updated this figure, and we see that some of the transects they go up north and some down south here. So what I didn't study this variability in the location. Instead, I wanted to show you how much of this mean transect represents the seasonal cycle. So it's one of the components that would influence the seasonal cycle. So we have it's generally 4 times a year the transect, and here we want to. It's the two aspects of this: the number of years sampled, 0 to 15, and the number of samples per year. That's it. We have 4 here, but we want to test from 2 up to 20 samples a year and see how we solve the seasonal cycle from that. So for this, we came up with this design plot here where we have the number of samples per year, so growing from 2 to 20, and the number of years from 1 year up to 15 years. And we see that generally as we go up and in the numbers here, generally the RMS bias reduce. So this is calculated first because we just have 6 years of model data. So this had to be resampled, and we created a 100 years time series just resampling and keep the same seasonality. And then so for example, for a set of parameters, 4 times a year for 4 years, we select 4 years of this 100 years and sample every time and calculate the RMS against that and the seasonal cycle and produce that 400 times so we can calculate the RMS. So we see that this star here represents where we are right now with about 20 transects along 34 south, and we see that we are pretty close to the maximum error here in the parameter space here. So this would represent like the seasonal variability that is not captured at all. And then as we have more number of years or more samples, we go to this to try to reduce the error. So we still have a lot to improve in this part. And yeah, and as I said, we want to go in this direction here, where we can reduce slope in the number of sample years, increase the number of sample years and the number of years. But we have this observational constraint here that we can't have like 20 transects a year for this because it costs a lot of money. So generally we go in this direction here. So increasing the number of years can be a good improvement for our data. But you see, for example, for 12 years, we improved from 1.7 TRMS to 1.4. So we need like 15 years of data at quarterly temperature.
Did you say why we got 10 years of data and the actual years are there? I believe it's 5.
Yeah, because I just got the transects that are close to the 34 south. If it goes to Rio or go to Patagonia, so I don't count them. That's close to 34 south. So that's this other uncertainty that could be addressed here, but it didn't take into consideration because of the model constraint. So on this spatial sampling, so as I said before, so these are the model velocities here. So from here close to South America to Africa, and you see that the higher variability is located close to the boundaries here. As generally, we have a higher sampling of 25 kilometers. And yeah, we want to, so we asked this question, is this a good approximation, the heuristic approximation of 25 kilometers in the boundary? So what we do is that in the reconstruction, we keep increasing the spatial sampling in each of the regions, and then compare against the perfect reconstruction. So this is what we get. So this in the x-axis is in degrees of longitude is the sampling space in between. So from the model resolution, you have 0.08 that is the native model sampling, native model grid, and we increase up to 5 in the 3 regions: western boundary in red, interior in blue, and eastern boundary in black. And calculate as metrics the root mean square error, correlation, and bias. So you see, if we start from the bias, we see that, for example, the blue line in the interior is basically zero bias. Doesn't matter how well you sample the interior, and most of the variability is you have an increased variability, increased bias when you decrease the sampling in the western boundary mostly, and in the eastern boundary as well. So there's a kind of a compensation with this because you have the Brazil current flowing south and then the Agulhas flowing north. So one kind of produce different bias in our sampling. And this is all them agree in terms of in the AMOC and heat transport. They kind of follow the same pattern. And you see that so the highest errors are in the western boundary. So in the western boundary, we have generally at 25 degrees sampling, and in the interior, the blue one, we have a 50. So this is what the errors we got in terms of the sampling we currently have. So the western boundary is the one that produces highest errors. So if we could improve the western boundary, something that would improve our estimates. So the last point I want to talk on this part is about the barotropic velocities in the model. So as you see, the barotropic component is generally has a really fast propagation patterns, and is generally associated with the bathymetry of the region. And you see that at 34 South we have a very wide shelf continental shelf break, and then we have the Walvis Ridge here, and we see that the barotropic velocities generally are associated with these features. And this is something that we can't calculate directly from the thermal window relationship, and we need to add information about these barotropic velocities. So one way to try to simulate it, so we can't go all the way to the model resolution to sample the model velocity. That would be unrealistic. What I try to do here is try to compare what if we had a climatological estimates of this of the barotropic component or the velocity at a certain depth. How this would improve our knowledge of the total, for example, AMOC and the heat transporters are just added for the AMOC here. So, and this could be estimated, for example, from Argo, climatology, or other estimates on the boundary. So, with that, here 4 cases in which first assume a level of no motion, so 0 velocities at 37.09. Sigma 2 is about 3,700 meters. And use the climatology in the eastern boundary, western boundary, and east plus western boundary. And in blue here is the barotropic component, and in red the vertical shear. So these are estimated from the perfect model decomposition. And the reconstruction is this gray one that I hope you can see. So the gray one for the vertical shear, it doesn't change. So so the vertical shear, as we expect, is not influenced by the reference velocity, right? Because you have zero integrated transport in the vertical shear component. For the barotropic component, that is mostly affected by the reference velocity. So if you use 0, we have a little bit of misrepresentation here. So you get a generally stronger AMOC because the vertical shear and the barotropic, they compensate each other. So if you reduce your barotropic part, you increase the total AMOC. So the eastern part seems that you get the best stream function mean here. And the western two, you have an improvement, but the eastern seems to be better. And when you add both, you get right almost on the top. And the bias is just 0.3 is verdicts. But this, I'm talking about the mean here, but the RMS is still high here. 4.4 is verdicts. I added this climatology. So the climatology can improve your mean estimates, but not too much on the variability. So the variability is based on what they had before when you have 0 reference velocity. So yeah, one of the methods we try to overcome this problem is try to use other observational data to improve our representation. This altimetry is something that we always use together with XPT, and is a good candidate for that. So we see that from previous work that if you have the total surface height and then you subtract the dynamic height calculated from your hydrography, salinity and temperature. So if you calculate this residue here, you get the non-stereo component, and that would be mostly the barotropic component. So if you calculate this and calculate your velocity, in the model, we see how for example, for this is in 2010, is one snapshot of the model and how this method would reconstruct it, and you see that does a pretty good job. Of course, we haven't used any observational error in, for example, would happen in a visual, and it's something that we are trying to do right now. So the dynamic height here, so this has to be fixed at some level, and then we estimate the dynamic height relative to that level. That is the typical geostrophic assumption. So we try here to estimate what would be the variability in terms of the reference depth that we estimated this residual, and we applied in the model at that same depth. For example, if I assume at 800 meters, calculate the dynamic height at 800 meters, calculate the velocities, and add that 800 meters in the model. So this is in terms of the AMOC stream function and AMOC strength and meridional heat transport. So we see that, and this is the depth of the AMOC in terms of correlation bias and root mean square error. And we see that so yeah, it starts for the bias here. So we see that the bias, generally, when you assume a reference level that is too close to the surface, you have a strong bias at about 4,000 meters here. And as you go deeper, you decrease this bias. And then up to a certain point here, and it's really close to the 3,700 meters that we use generally for the reference depth. So this seems to be a good candidate for the best approximation we could have. And if you go in terms of AMOC strength and heat transport, we see that the correlations are pretty high using any reference depth. And of course, at 3,700 meters, we seem to have a highest correlation, and bias close to 0, and the RMS 2 is below 2 meters. So before we had for the climatology, we have almost 5 isoverders of RMS, and here we reduce for less than 2. So it's a good improvement if we really estimate from that. So these are all the error estimates. I didn't go through all of them, but you can see that the western horizontal resolution and the reference velocities, they carry the biggest error towards the other components. And so these are something that we can improve in the methodological sense. Some we can't, like a non-synopticity of the data or mass imbalance or hydrographic edges, that we can't improve on that part, but this probably we can. So, and the last part here, try to go quickly, and so this is how the XBT measurement errors affect this estimate. So we know that the XBT doesn't measure direct depth, so it estimates the depth from an equation depending on the time of the descent. And also, it has a thermistor that measures the temperature changes that generally carries up to 0.2 Celsius of its accuracy. And a depth offset is generally related to the entry velocity and the height from the ship that is dropped, and so it relates to surface problems. And the depth linear bias, so this would be kind of a linear approximation where we have the offset and the slope. And the depth bias is related to pure fall rate equation, and so is the equation that calculates that estimates the depth. So it's about 2% of the depth. So at 700 meters would be 400, or it would be 14 meters the error. So if you have the temperature error here in the section, we see that this would affect mostly between 400, 500 meters to up to 800 meters. And how would this influence our estimates of the AMOC and heat transport? So we use the same model approximation. We resample the time series all the way to 1970. So this would be, so we did that exactly to avoid the interannual and decadal variability, so we have a more robust, really Gaussian error. So this is how we approximate them. And so we add all the three tolerance errors from distributions given by the manufacturer, and we see that the errors, how these errors compare with the variability of them. The variability of the AMOC and the heat transport is here in gray, and just the errors, the residuals, would be here. So would be about 3%, 8%. So it generally agrees with the other errors we estimate, but it generally is smaller. So just about 0.38 value. So it's not a big deal for these estimates and compared to the other ones. So here, go quickly here, just so we can also compare in terms of the heat transfer in terms of the overturning and gyre components. Generally, the overturning and gyre, they compensate each other. The gyre is negative, and this agrees with the work by Donga. And so this is the variability, and this is the variability of the errors in black. So the black is, we see that most of the errors are due to the overturning parts, and is smaller here in the gyre. So it's proportional to the strength of the components. And also here, I'm not sure if you can see the green one. So it's in the velocity errors associated with the so we have temperature errors and then translating to velocity errors. These are the ones that carry most of the uncertainty in the heat transport. So the temperature error is not too much, but kind of compensates a little bit. And so when we add both, is a little less than the velocity only error. So, but the thing is that these errors are not random distributed. They vary over time. And this recent paper, Collier et al. 2013, they measured since 1970 to 2010 how the errors, the depth linear bias, the depth offset, and the temperature offset, how they vary over time. And then we see that especially the depth linear bias is in a strong phase right now. The errors estimated, so these are estimated from XBT and CTD comparison collocators. And the depth offset seems to be more or less steady, and the temperature offset has this big drop here. And so when we estimate the residuals in the AMOC, we see that the depth linear bias is off control most of the bias here. And we see by the relationship between the error parameters and the AMOC residual, we see that the depth linear bias is what controls most of the uncertainty. And so here's, if we add all the uncertainties together, and we see that can go up to 0.4 petawatts and 0.3 petawatts and almost 0.5 volts. And we have a really strong relationship between the heat transport and the AMOC. This is similar to what has been estimated in other studies in the region. This regression here between AMOC and heat transport. And if we look at how, because this is very noisy here, because they call it all, they give a mean and a standard error estimates of the error. So when we simulate that, we have a highly noisy variability. So one method to filter this variability and to see how it changes over time, we have this, we just apply the cumulative sum of these time series here, and we see that how it varies over time. And we have a peak down here, exactly 96, 97, exactly when SIP can change the factory to Mexico and change some of the coating in the XBT. So we have a climate signal from the Mexico. So generally, the historical bias since the 90s can be 0.3 varieties a decade and 0.02 is when. So these are the bias, and how does it compare to the bias that we see in the AMOC? How would this be significant or small? So I try to address this by comparing to some of the estimates, historical estimates up to 1970. So of course we don't have observations by then, but we have reanalysis. Right? So for example, for the soda that goes all the way down, soda it doesn't have the resolution of the hyphon, but it goes all the way down to even previous than 1970. So try to estimate this trend. The decade is like 0.1 is variable per decade of the Meridional the AMOC, and 0.006 for the parallel. So adding this over time is not statistically significant, and that's what we want to show here in this last plot. That so to understand how the bias due to XBT compared to the historical bias, for example, in the AMOC or the heat transport, we do a histogram of the residuals for each decade, 97, 8, 9, 2000, 2010, against the control variability of the hyphon model and the trend estimated by SODA here in dashed line. So let's go one by one here. So of course, in the control simulation, we assume zero residual and a variability given by the variability of the AMOC and the variability of the heat transport. And we have this distribution here. So the distribution englobe the three first decades of the 70s and 90s are within the uncertainty of the variability of the AMOC here. So they are not statistically significant. So this trend in the beginning of the time series, they are not significant. But when you go to 2000, 2010, where we have the highest rate of the biases, we see that they don't overlap the control time series with the bias estimated for these two ones. So these are probably statistically significant in comparison to the mean AMOC. And this is the bias estimated by SODA after 2000. So by SODA doesn't give a statistically significant either. It's a very, very wide and overlap with the control here. And the same for the heat transport. So we want to make a point that although this trend is small, over time, the trends associated with these biases can affect our detection of changes of the meridian over time. So yeah, so I don't know. I think I talked about all the conclusions, but so some of the sampling, the quarterly, the spatial and temporal sampling, is something that we can improve, of course, due to operational constraints. But probably the spatial sampling, we could probably increase the western boundary sample by 20 kilometers and collect more data in a quarterly sampling up to 15 years of data. So 15 years of data on the top of the mean section. Right? And so the TF padding and salinity estimation, we should try to estimate the salinity on the top of 800 meters from monthly average or comparable or something to estimate the salinity like that. And the barotropic mode is one of the highest uncertainties in the model. Probably 3,700 meters is a good representation for the level of no motion. although there are errors associated. And the satellite altimetry could be one good approach to improve this methodology and barotropic component estimate. Thank you.
Marlos, I have a quick question. It seemed like the mean salinity versus what you think will happen, it had a big difference on the seasonality of the geostrophic, or was that, is it a big difference? Is the seasonal cycle that you would get from the model in terms of the geostrophic contributions to the AMOC, is it very different if you have the mean salinity or?
That just reduce the variability, but doesn't change it. Yeah. One of the objectives here was trying to see if we could change the seasonal cycle and what would affect. And generally, none of the approximation would change drastically. That the only one that could is the barotropic. If you assume that you have the barotropic component, because the barotropic has a big seasonality there associated. If you don't account for that, you could have maybe the whole geostrophic part there.
I use Western sunrise though. It's like something very wrong, and I think that you made it not very efficient. It's like
right.
You go to the Western major point, of course. Western.
The major point.
So Western is the sunrise.
We should continue monitoring that with this data.
So this is the data simulating model, right?
Yeah.
Still trying to figure out why the reconstruction physics from the actual model true. So, I mean, it's possible to sequential data simulation, which I think ICON is, right? It's not agile, but no, you can be introducing kind of dynamical imbalances at certain times that you mentioned.
Yeah.
So, what might be calculated as geostrophic, might not really be geostrophic to the model assessment.
Right.
Forcing hasn't happened yet. So, do you think that that's important in that at all, or is it just a free running?
Yeah, no, I believe that would impact it. I haven't done with another model. I want to do that with maybe the HICOM reanalysis or another one that does free running. Yeah, so that would be better. But generally, all the components I take off the flow imbalance of the section to calculate each of the components. But I know that
You mean that mass transfer?
yeah, the mass transfer.
But I'm talking about maybe thermal wave profile.
Yeah.
Just sort of shear profile might be got a bunch of density.
Yeah, no, I believe so too. Yeah.
These procedures supposedly tend to make cases for example multivariate, so that's what's supposed to not do too much, but maybe it does. That's a good feedback for the Navy who did this analysis.
Right.
Do it on the same model, free running, different reasons.
Yeah, that could be.
Marlos, can you go back and go further conclusion?
Let's see if I
You said you need a continuing 15-year observation for what? For capture seasonal variability?
seasonal only.
Only for the seasonal.
Yeah, I just look at the seasonal. Yeah. Because the seasonal is.
So you continue observe for 15 years, if you need the area will be smaller. This is what you need?
Yeah. But this has some assumption of the steady, right? You have a steady AMOC. And so if you change over time, you will probably change your seasonal cycle to it. So yeah, there's a lot of approximation this.
Yes,
this part.
yes, I agree with this, but however, from a climate point of view, you need a longer. 15 years, not enough. You need longer.
Yeah. No, I think so. Yeah, just to solve the once we solve the seasonal cycle, can estimate the interannual variability, right? But we first need a good seasonal cycle. Okay.
I have a 15-year proposal to do that. You had a 15-year proposal.
Yeah. Was longer. Was longer.